So hopefully this session will be useful not just for this course, but just generally. It's a common it's a common area of confusion. So we'll go through a few things in this example sheet. So let's see who else we have. Oh yeah. There we go. So we'll do our normal thing and let a few people dial in. This session and the next two sessions will probably be the most important ones of the course. So I'm glad you're here. Just to let you know, as usual, we're recording the sessions, and hopefully you can. Was everyone able to get the previous sessions if they needed to from Blackboard and from YouTube? I guess you guys all dialed in, so you didn't need to.
Yeah, I haven't tried to watch them.
Yeah. Okay. So we have a few people in. Not many yet. I'll give it another 2-3 minutes. I'm going to trim the beginning bit. If anyone has any questions before we start, I'm going to trim this little bit off. So before I upload. And I do encourage you folks that are here today, do dial in on the Wednesday sessions if you have any other questions. All right. So we don't have many people in today, but we'll let people dial in one more minute and then I'll kick off. Okay then, so this is week 8, so we're going through the week 7 problems. The week 7 problems, the first 2 questions are fairly straightforward, I hope, but they're just to get you there to practice obtaining the plasma frequencies and number densities. And our first question was using the D, E, and F Earth ionosphere plasma frequencies given in the notes. Calculate the electron densities in these layers and the cutoff frequencies and wavelengths for transmission through these ionosphere layers. And the purpose of doing this question was to make sure that you're happy and familiar with the conditions on a plasma which allow radiation to either be transmitted or reflected, and what happens to the radiation if it is transmitted. So the first thing we'll do is we'll explicitly calculate the number densities and the cutoff wavelengths. So the first thing is, of course, the cutoff wavelength is the same. Goes with the cutoff frequency, and of course, the cutoff frequency is the plasma frequency. The plasma frequency is the cutoff frequency. So the cutoff wavelength is just C divided by whatever the plasma frequency is. So for our 3 plasma frequencies of 310 to the 5, 310 to the 6, and 310 to the 7, the cutoff wavelengths are 1,000 meters, 100 meters, and 30 meters. But it's important to realize that these cutoff wavelengths are the free space wavelengths. So we imagine that the radiation is propagating in free space with a certain wavelength. And if it encounters a plasma such that the frequency of the radiation is below the plasma frequency, so that the wavelength is longer than the plasma frequency, sorry, the plasma wavelength, then the radiation is completely reflected. However, if the frequency of the incoming radiation is above the plasma frequency, then the radiation can penetrate the plasma. And when the radiation penetrates the plasma, there are 2 other physical phenomena which occur. The first of them is that the wavelength of the radiation within the plasma is different to the free space wavelength. The second thing which occurs is that the radiation is traveling through the plasma and it is encountering charged species within the plasma, both ions and electrons. And let's assume that the ions and the electrons have the same charge. This could be, say, hydrogen gas is a very common plasma material. We have hydrogen gas. The electrons and the ions experience the same electric field and the same force, but the ions accelerate much less. So because of that, their acceleration is much lower and therefore they radiate much less. So we only have to worry about the radiation that the electrons in the plasma are emitting. And we recall, don't we, that with the electrons in the plasma, in the same as any other freely moving electrons, if those electrons experience an electric field and are accelerated periodically up and down, they will radiate, and that is scattering. So the electrons in the plasma will scatter the radiation that is passing through them. So let's depict that, and I'm going to put this notebook onto Blackboard after this session. So I'm calculating here the plasma frequency and density that correspond to a number of different cutoff wavelengths. So just to remind ourselves that the plasma frequency squared is proportional to the number density of the charges. And we normally think about the number density of the electrons because it's the electrons that are doing all the interesting stuff. So the plasma frequency is the number density of the electrons with some scaling factor. And of course, if we use the correct units, and this unit is either 9,000 in the denominator or 9, depending on whether we're using giving n in per centimeter cubed or in per meter cubed, the number density is just the plasma frequency squared divided by 81 if we're giving the number density in per centimeters cubed. And the reason why I'm giving you all of this in both centimeters and meters is to get you to practice converting between those numbers on a regular basis. So the number densities we obtain, of course, is that the plasma frequency rises, we have a larger number density. And the number density rises more rapidly than the plasma frequency does. Okay, so let's plot that. Here we have plasma frequency and density, and you will probably do this yourselves in Python, but I prefer to do it in Mathematica here because I can show explicitly that the formulae are exactly as we're saying in the notes, of course. And I find it useful as well, and this is a tip for you, to define the constants as a list here. So you can see I've got the speed of light at the top, I've got the electron mass. And I also define useful units. So I define a centimeter. So if I type in 4 centimeters, then it will give me the number 4 times 10 to the minus 2, which is very handy, as we shall see next week, in keeping track of converting sizes when I'm calculating various physical quantities, like how the size of a waveguide gives rise to a certain transmission frequency. So anyway, so I go down here, scroll down, and what am I looking at down here? Plasma frequency. Here we are, plasma frequency at the bottom, and I've calculated here a line which is the cutoff wavelength as a function of electron density, where again I noted carefully during the lectures that I'm giving this in per centimeter cubed. So of course this horizontal axis will be different if I show that in per meter cubed. And again, if the frequency of the incoming radiation is below the plasma frequency, then I have full reflection, which means of course long wavelengths, which is above this line. And you can see here that the typical electron densities we were talking about in our ionosphere were of the order of 10 to the, what was our numbers? About 10 to the 5 or 10 to the 6. So we're down here. So you can see this is, in roughly speaking, the radio wave to microwave region. So radio waves and microwaves cannot penetrate through the ionosphere, whereas visible light can. So visible light is down here with about 1 micron wavelength, and that can pass through the ionosphere and also through the air below, which of course is why we see it. But the electrons in the ionosphere layers give rise to scattering as the visible light passes through them. So we see scattering in the ionosphere due to the electrons, and we also see scattering at lower altitudes due to the presence of the air atoms as a whole further down. So I'll add on those points. Here they are. So those are the explicit points, and of course they lie as they should do on that line. Okay, so that's the plasma frequency and density. That's a fairly straightforward question. Now the next one is to plot in Python or something else I'm going to show again in Mathematica, that we get the correct shape of Thomson scattering cross-section varying to the Rayleigh scattering and other cross-sections as we change frequency. So where is that got? Where is that gone? That is here. Okay, so that, again, I shall put this onto Blackboard. And again, it's always good to try to plot these to see how things vary as I vary parameters. So I'm going to here just quit the evaluation. Okay, and run the whole thing from top to bottom. And the part of the expression that I'm plotting here is the omega to the fourth over omega naught squared minus omega squared squared. Okay, from there up there, plus omega squared gamma squared. So I've labeled gamma as G and omega as W in this expression. And I'm calculating the variable part of the cross section. And I've ignored the prefactor, which is the 8 pi r naught squared over 3, because obviously that would make that term, that would make the overall cross section quite small. So I'm just plotting how this varies, and I have given the resonant frequency to be 1 unit, and the width to be 0.2 units. So this is in units, some unit frequency. It might be megahertz, it might be 100 megahertz, whatever I like. And of course I can plot it, and it rises up from 0 to some peak value at the resonant frequency and then falls, of course. And you can see here that at 0 frequency, the cross section falls to 0, whereas at high frequency, it tends to a certain value. And of course, this should be 1. Well, let's see what it looks like. What we'll do is we'll calculate sigma for some very large value. Let's see what it is for a large value of, say, 100 times W0, 100 times the resonant frequency, and it falls back down to about 1. In other words, it falls to the Thomson cross-section value. Does it fall even closer? Yes. So as I go to very large frequencies, the cross-section falls to something like the Thomson cross-section. Okay, so that's at the high frequency end. And we should probably look at the low frequency end. Well, the first thing to do is let's change that to a log plot. So we're now plotting this on a log axis, and again, you can see that there is a peak, and the cross-section asymptotes to a value of 1. And as you can see here, the cross-section falls to a very small value at very low frequencies. So there's very little scattering at low frequencies or at long wavelengths. So what we want to do is we want to plot this in a slightly clearer way. What we could do is a log-log plot to zoom into that. And you can see it looks like some kind of straight line, which means that this is following some kind of power law. There's a power law relating at low frequencies between the frequency on the x-axis and the scattering cross-section on the y-axis. But it's hard to see from this plot what that looks like. Now we know it ought to go as omega to the fourth. Okay, so let's plot the cross-section to the 1/4 power and plot that as a function of frequency. And that's what we're plotting here. Okay, so we're plotting the cross-section versus omega. Okay, so I'll just eliminate that last one. I'll put that to 0 for now. So you can see here, this is the cross-section as a function to the 1/4 power as a function of frequency up to half the resonant frequency. So let's plot that to a higher frequency. You can see if I go to a higher frequency, this curve starts to deviate away from this linear behavior. So this linear behavior at low frequencies is telling me that I have a behavior of the cross-section which goes as omega to the fourth, and therefore at low frequencies the scattering obeys Rayleigh's law, which is that the scattering goes as omega to the fourth. So I'll go back down again to plot from 0 to 0.5, and I'll show what this straight line behavior looks like, and that's the yellow line here. So I can see directly, I can zoom into lower and lower frequency ranges. Here I'm plotting from 0 to 0.2. You can see that the deviation of the cross section away from the Rayleigh behavior is still rather small, even when the frequency of the radiation is already 20% of the resonant frequency. Okay, so that's what this plot shows us. Now, of course, the other thing we can do is we can change the width of the gamma value. So let's do that. So I'll try plotting. I'll go back to an ordinary plot here. Okay, so there's our peak, and now I'm going to change the width of the resonance. So this is now 0.3 times omega 0, and of course I can change omega 0. So in reality, the width of the peak will be much smaller than the resonant frequency. Okay, so this would be more like 100 really, and really I should be plotting between, say, 90 and maybe 110, and that's what the cross section will really look like. Okay, so at low frequencies we'll still have that Rayleigh behavior, and at high frequencies it will still asymptote to 1. So we can plot that. We'll do that on a log scale. Okay, so you can see that the cross section falls to 0 at low frequencies and it falls to 1 at high frequencies, but around the peak, I'll zoom out a bit, go to 50 to 150. Okay, you can see I now have that rather sharper peak where I get this resonant absorption occurring. So you can play around with that plot, or you can use your own plotting code. Right, now that was just for a bit of fun. Now let's, and by the way, any questions as normal, please put them in the chat. I'll just see if there are any. Okay, now, the next thing was to look at the rate of scattering as a function of depth. So I hope you found, if I go to Lily, yeah, if we go into Blackboard, I've put rather poor scan actually, but I put a scan of section 6. We're looking here at nuclear collisions. And the reason I've asked you to look at this, of course, it's very relevant to doing calculations of scattering rates. And it's a commonly misunderstood part of general physics. So the bit we're talking about is the cross section and the differential cross section and the reaction rate. And there's a number of different ways of writing it, but the most important equation is equation 122 in Lilly, where phi is the incident flux of some set of particles. Sigma is the cross-sectional area of the individual things that these particles may hit, and n is the number density of those particles per unit volume. Okay, so phi is a flux per unit area, and r is the number of things which interact. Now it's important to know that n is often given as capital or little n, and I've adopted capital N in the notes to distinguish it from the refractive index, but normally it's given as a little n. Okay, so just be aware of that. And here's a picture of what it looks like. So here are my atomic objects, and they lie within some volume. And of course, when I think about the effect that they have on absorbing a beam of particles, we tend to think about little pieces of thickness. So I imagine a certain intensity of incoming particles. That's intensity I. That's the same as that flux phi we saw before. And I imagine little absorbing objects, and these have an area sigma, and there's a number density n of them, little n this time. And you can see that we can obtain little n if I have a certain physical density of atoms, say, which is what we're going to be talking about in our question about the nitrogen gas. I can convert from the molecular mass to the number density using our conventional rho Na over m formula. So I can calculate n sigma, which is representing the likelihood that a given particle will see one of these absorbing objects when traversing a unit distance. So the rate of absorption per unit distance is n sigma I. And of course, if I now make an equation out of that the rate of absorption is di by dx, I can recover, of course, my exponential absorption law. Now I can look here, this exponential absorption law, and I can see that n sigma is a characteristic rate. Okay, so if 1 over that is the mean free path. Okay, so the intensity goes as e to the minus x over lambda, where lambda is the mean free path, and I can identify the mean free path as being equal to this thing, capital sigma, and we call this the macroscopic cross section, and of course it's dimensionally it's just equal to the microscopic cross section sigma times the number density. So all absorbing situations obey this sort of law, and of course this is why the exponential absorption and exponential reduction of intensity occurs in most materials. Now, as well as considering sigma as being an absorbing process, we can also consider this for scattering. So if I have a scattering object, an incoming particle will collide with this area sigma, and it will give rise to a scattered particle in some arbitrary direction. And we consider that event to have occurred, and the outgoing ray goes in some particular direction. My outgoing photon goes in a particular direction. So that's what we're doing here. We're calculating in question 3. Our situation is that of 10 keV photons traveling through air. So this is our air here with individual atoms with some area. And at room temperature, we know what the pressure will be, so we know what the number density will be. So we're going to calculate that in a moment. But the effective area of the nitrogen atoms have an absorption cross section of 82 barns. Now, I noticed that when I posted this up, I put this down as 10 to the minus 28 centimeters squared as well. I apologize for that. 1 barn, of course, is 10 to the minus 24 centimeters squared. And we're going to use a barn as a very convenient unit. As you can see, it often has values around about 1 as opposed to 10 to the minus 28. And we're going to use this photoelectric absorption cross section, and this is the area of each atom in the nitrogen as it presents itself to the photons. So this cross section applies to each nitrogen atom. So the first thing we need to know is how many nitrogen atoms do we have in the air? So that's the first part, is calculate the density rho. Now this is useful to do for another reason. So let's look at the worked answers. So nitrogen, of course, is molecular. There are 2 nitrogen atoms per molecule, and to calculate its density, we recall that it has a mass of 28 grams per mole of nitrogen, and that 1 mole occupies 24 liters. So 2 commonly known facts that you will know about nitrogen allow us to calculate that the density of air is 28 divided by 24 grams per liter. And that's a very useful number to know. Okay, it's about 1 gram per liter, or about 1.1 times 10 to the minus 3 grams per cubic centimeter, which is about 1,000th the density of water. So it's a very useful number to commit to memory, that air is about 1,000 times less dense than water, so that if I boil a kettle of water, which contains 1 liter of liquid, it will turn into 1,000 liters of air if I allow it to expand in an unrestricted way, i.e. at 1 atmosphere. So I can now calculate the number density n, capital N this time, of molecules per cubic centimeter is 2.37 times 10 to the 19. However, there are 2 atoms per molecule. So the number density of the atoms is twice that. So correctly calculated, it's about 4.73 times 10 to the 25, and I've now gone to per meter cubed because I've multiplied by 10 to the 6 from per centimeter cubed. So I can now calculate, so this 82 barns here applies per nitrogen atom. So per nitrogen atom, the macroscopic cross section is just n sigma. So the microscopic cross section is the effective area of each atom, which is 82 barns. The macroscopic cross section is 0.388 per meter. So they have different units. One is sigma's meter squared, little sigma's meter squared, and big sigma is per meter. So again, it's useful to calculate these in both unit systems because I think it helps the inside. So capital sigma of 0.388 per meter is 3.88 times 10 to the minus 3 per centimeter. So that means in each meter, there's a probability of about 0.4 that a given gamma ray will be absorbed by a nitrogen atom. That's what capital sigma means. So therefore, the mean free path of the gamma rays is about 2.58 meters. So obviously, if I'm going to attenuate to 10%, which is one of our calculations later on, I'm going to need more than 2.58 meters of air. Okay. Now, let's confirm first that the so-called mass attenuation coefficient is 3.53 cubic centimeters per gram. Now, you may or may not have encountered the mass attenuation coefficient. It online is given in a slightly confusing way in a couple of places that you will find immediately. The mass attenuation coefficient is equal to the linear attenuation coefficient divided by the physical density of the material. And this linear attenuation coefficient is the same thing as the macroscopic cross-section. They're the same thing. That can be a little hard to find. Another way to look at it is to simply look at the units of the mass attenuation coefficient here on the question sheet. It's giving in centimeters squared per gram. So to obtain the mass attenuation coefficient, I simply have to combine the density and the macroscopic cross-section in such a way that I obtain something which has the correct units. And I simply divide one by the other, which is what I'm doing up here. So the macroscopic cross-section is 3.88 times 10 to the minus 3 per centimeter. And the density is just 1.1 times 10 to the minus 3, which is 3.53 centimeters squared per gram. So if I want to work out what the reduction of the intensity is as a function of distance, remember it follows what we had here. We have a mean free path and I have a distance traveled. If I want to work out the intensity as a function of distance through the air, I can write it in one of three ways. I can write it in terms of the mean free path lambda. I can write it in terms of the macroscopic cross-section sigma, or I can write it in terms of the mass attenuation coefficient, that's mu mass, and of course to convert it back into the macroscopic cross-section, I multiply by the density. And the reason it's written this way is in case I have an absorbing material where I make that absorbing material have a different density. So now I can use the same mass attenuation coefficient, which is a property of the atoms, and I can scale it for different densities. And of course, our job here is to calculate the distance over which it drops to 10% of its original value. And it turns out that this number is about 6 meters. Okay, so that's how we do it for X-rays. Okay. Now, so you can see here that the rate of absorption, is given by the number density of the atoms. And you can see if my number density was 1 in some volume, then the rate of scattering, so the rate of absorption would be much, much lower. So that's of course relevant when we think about doing a laser pulse focused onto a plasma. So we have a different physical process here. So here we have the situation of Thomson scattering. So this is the same as one of the examples on section 4, the end of section 4. I think it's example 4.4, I believe. So we are thinking about laser light, which is focused onto a small quantity of plasma, onto a cubic centimeter of it. And we're given that the free electron density is 10 to the 18 per cubic centimeter. Now, to start with, we want to figure out what kind of scattering this is. So we should probably check that it is actually Thomson scattering that we are dealing with. It is likely to be Thomson scattering because the photon energy is small. Okay, so remember that in order to calculate the photon energy, the energy of a 532 nanometer photon is about 2 electron volts. And 2 electron volts is much less than the electron rest energy. And therefore, there is no significant transfer of momentum from the photon to the electron. So therefore, this is Thomson scattering. Now, because it is Thomson scattering, what we're now dealing with, we can think of the scattering as being the photons, the visible photons, giving rise to an electric field which accelerates the electrons up and down inside the plasma, causing them to re-radiate. And again, we remember that in a plasma, the electrons are being accelerated much more than the ions are, and therefore we can forget about the ion motion and the ion acceleration. The radiation from the ions is very, very small. So the electrons are being accelerated and are radiating, and the radiation is in all directions, and the scattered wavelength is equal to the incident wavelength. So that's just 532 nanometers. Okay, so the rate of scattering, which allows us to calculate the power in the scattered radiation, is determined by the Thomson scattering cross-section. So just to remind ourselves, the Thomson scattering cross-section is proportional to the classical electron radius, which is 2.8 times 10 to the minus 15 meters. And a good number to remember is that the Thomson scattering cross-section is 0.66 barns. So again, the barn is a useful unit. So you can see here that the Thomson scattering cross-section, the rate at which these visible photons are being scattered by the electrons is, in this case, a lot smaller than the likelihood of the X-rays being absorbed by the atoms, by the electrons in the atoms. Now, the number density we're given here is 10 to the 18 per cubic centimeter, which is 10 to the 24 per cubic meter. And again, just as we did before, to work out what the macroscopic cross-section is, we simply multiply the cross-section for the electron times its number density. So it's 6.6 times 10 to the 5 per meter. So the mean free path of the laser photons in the plasma is 15,000 meters. So of course, this is much bigger than a cubic centimeter. So therefore, there is no significant attenuation. So the intensity of the rate of the visible light passing through the plasma is not reduced in any meaningful way whatsoever. So I don't have to worry about it in my calculation. Now, how do we calculate the power? Well, you can see that the power that's scattered must be proportional to the incident power density. Here we are. So here's our formula. So if S is the power density of the incoming visible light, then the scattered power is just equal to the Thomson cross-section times the incident power density. So again, our unit conversion is S is in watts per meter squared, sigma is in per meter cubed, and power is given in watts. But this is the power given by one electron sat in some kind of electromagnetic radiation passing over it, which has some density per unit area. So we imagine some power being focused onto our cubic centimeter of plasma, and it will re-radiate in a number of directions. And we have 1 cubic centimeter, and our number density was 10 to the 18 per cubic centimeter. So therefore, we have 10 to the 18 electrons. And again, as we said before, we have the same number of ions, presumably, and there's no acceleration and no radiation of those. So the ratio of the incident power density to the scattered power is 10 to the 18 times the cross section for 1 electron, because I have 10 to the 18 electrons. So that number is still, again, very, very small. It's about 6.6 times 10 to the minus 11. And of course, this number here should be consistent with our idea of the mean free path. The amount of power that's scattered must be a small fraction of the power that's been focused onto our fusion plasma. So let's take our example 4.5 numbers. So our incident power, let's pick an incident power, which is say 1 megawatt. So I've got a 1 megawatt laser. So that's the incident power, but I focused it onto an area of 1 square centimeter, which is the end of the plasma cube. So the power density is much, much bigger than 1 megawatt. It's now, of course, 10 to the 10 watts per square meter. So the radiated power from this formula is 0.66 watts. So you can see an important fact that if I were to focus the laser onto a smaller spot, then I would get a greater amount of power if I was also able to squeeze the plasma into a smaller volume as well. So that's worth bearing in mind, that just because I focus onto a smaller volume does not mean I get a larger power. So because whilst the power will increase, the power density will increase, that's S, the number of electrons that I'm illuminating will reduce, but it won't reduce in the same way because, of course, I still have a certain thickness. So there's no global conclusion I can draw. I have to calculate it case by case, but merely focusing the laser onto a smaller spot does not give rise to a larger scattered power necessarily. Now, these are typical numbers. A 1 megawatt laser is a fairly common or garden laser power that I can fire every so often. And you can see that I get a small fraction of that re-radiated, maybe 1 part in 10 to the 6 is re-radiated. And this radiation is in fact possible to measure. 0.66 watts is possible to measure, even though I'm only collecting it. Remember, that's the power in all directions. So the power observed into some small aperture. Let's say you imagine a plasma vessel, which is maybe 1 meter away. I will observe a small fraction of that, but it might be, milliwatts. I might be able to see milliwatts. I can measure milliwatts of radiation. Now, one last thing here is to think about whether what the nature of the radiation going in and out is. Another thing to check is that the light can actually penetrate into the plasma. Well, let's calculate what the plasma frequency is. My plasma frequency, when given in when I give n in per centimeters cubed, which is what I've got. So the n in per centimeter cubed is 10 to the 18. So 9,000 times the square root of 10 to the 18 is about 10 to the 13. And that's my plasma frequency. That's my cutoff frequency. My laser frequency is about 10 to the 14 hertz, which is way above the plasma frequency, which means that my laser light can penetrate the plasma. It isn't reflected. So that's one thing I can calculate. The other thing to wonder about is the polarization, the nature of the polarization of the radiation. So if the incoming laser light is polarized, then the scattered radiation is also polarized. So by measuring the polarization of the scattered radiation, I can also measure indirectly the polarization of the incoming laser, in case I wasn't able to measure it directly. So that tells me that if the laser light is, say, vertically polarized as it comes into the plasma volume, then no radiation is scattered up and down. It's merely scattered in all directions in a plane perpendicular to the polarization direction. Conversely, if the laser light is not polarized, then the radiation is given off uniformly in all directions.